Thank you so much. Thank you, Daniel, for inviting me over. Thank you, everyone, for being here on a Friday afternoon. And I apologize for this to be a Friday, but I had to teach the Wednesday, and so that took some time to come over and not be stressed out. So, indeed, we recently moved the group over from Harvard to EPFL, where I'm heading the laboratory for energy materials. And energy materials is what we find interesting, but I'll also propose a little twist to those energy materials that has useful consequences for the applications that we try to make better. And we really want to go today through how we map and track charge, then spin, and in the end, light polarization in emerging solution-processable semiconductors. So, as I said, laboratory of energy materials. So what motivates our researchers really to work towards a more sustainable energy future? We want to work on two sides of the energy equation. That is to say, yes, we want to become greener and more sustainable in the way we produce energy. And here I do see solar as the leading future technology. But also we want to become better and more efficient in the way that we consume the energy that we have at hand as society. And here we really moved from the age of industrialization to the age of, I guess, electronics still, but ever more so now we move towards the age of photonics, actually, and approach the age of quantum information perhaps one day as well. So really, today it's more about lighting and displays, the very smartphone display in your hands, the internet that you're connected through the optical fibers, perhaps, and really the way we compute, store information is becoming the biggest growing energy consumption sector, actually, in the next decade or so. So really, we have to become better in the way we compute and store information as well. Now, what combines all of these applications from the energy generation to the consumption side and all these photonic and information technologies is their materials backbone, and that's to say, semiconductors. So materials that interact strongly with light by absorbing them, turning them into a useful current in the solar cell, by recombining charge carriers in them to emit light, the display perhaps. So we really want to work here at making semiconductors better and teach them new tricks to become ever more efficient and perhaps have new functionalities to really help solving our energy balance, our energy future. So my group for this has a rather holistic, overarching approach, which combines materials chemistry. So we make new materials, for example, these chiral materials, these halide perovskite semiconductors. Then we do a big chunk of spectroscopy, and in particular, ultra-fast magnetic field temperature and polarization-resolved spectroscopy, which we also more and more now develop in my group. And towards the end of my talk, I will show you a few of those recent technique developments. And then we use such tools to do something I relate to as or call materials engineering. So we take an existing material platform, say a halide perovskite semiconductor structure, and then we imbue it with new functionalities, for example, by adding magnetic impurities, by playing with the degree of quantum confinement, or by twisting its surface to make it chiral, and really add something new to what this material can do. And all of this is then meant to inform the application space, again, towards very efficient solar cells, displays, or even quantum information technologies in the future, perhaps. So today will be mostly a spectroscopy and not so much a synthesis-heavy talk, but we also do work on that. And I'll really do a little tour de force between different application spaces as well. But because Daniel mentioned it already, I want to briefly showcase why I think right now it's very interesting to think about the twist in these semiconductors, and that has to do with the concept of chirality. Now, you are well familiar with the concept of the handedness of an object because your very left or right hand is chiral, meaning you cannot superimpose them on top of each other. They are looking very similar, they are mirror symmetric, but they are not identical. So this is what makes an object chiral, this lack of higher order symmetry. And while this makes sense for a chiral molecule, for example, you might be familiar with the concept that such a left-handed molecule might be curing a disease, whereas the right-handed enantiomer might actually be a toxic component for you, or compound for you. You might be less familiar with the concept of chiral light, and the fact that also light can be chiral, can be left or right and circular polarized in its properties. So this handedness of a chiral material, say a chiral molecule, does not have profound consequences in nature and in biology, but also extends to our optoelectronics that we are interested in. And this, for example, could lead to very efficient applications. For example, a lot of displays right now, the majority uses anti-glare filters, which is a very nice addition for you to actually see your smartphone display during ambient conditions, for you to not be blinded by the very sunlight that gets reflected from it and would come into your eye, and you wouldn't see a thing on your smartphone. But that very anti-glare filter is also, and it is based on a polarization filtering, is also holding back 50% of the light that would want to be outcoupled from your LED to begin with. So if you were to instead make this light into being circular polarized, you would actually overcome this filter, and that means you would have a boost of a factor 2 of your light outcoupled from such displays. So this is a very much mundane and economically driven motivation of why I want to make my light emission to be chiral. Further down on the horizon might be this a bit more diffuse concept of quantum information technologies. And by that, I simply mean the relationship that such a circular polarized quantum of light, such a photon, carries a defined spin angular momentum. It carries information. It's left and right-handed, just like an electron spin is spin up or spin down. And interfacing these two would really mean you have a spin photonic interface where I, for example, absorb this left-handed photon to create a spin up state and not a spin down state, or right-handed one, and vice versa. So absorption and emission of circular polarized photons then provides actually means towards optically addressable spin qubit writing and readout. So this is what connects us ultimately, I guess, in our motivation to understand such materials. For me, it's about understanding their polarization response, and it's intimately connected to their spin dynamics as well, as you will see later on. So this is kind of closer to economics, and this is further down on the horizon, but both are very interesting reasons to research this. And there are many more applications. You can, for example, think of anti-counterfeiting applications where you can have an additional layer of security by looking at whether the polarization state and not just the color of your banknote encoded security ink is actually correct. You could think about this as an extra layer in high contrast microscopy. So there's many other ideas. Really, encoding an additional layer of information in polarization would be desirable. So this is what motivates us right now to understanding these materials. And really, this is also the problem. There's a plethora of materials you could understand or try to understand, and there's a plethora of mechanisms that we try to unravel. And those mechanisms are needed to be understood to enable all such beautiful applications. But really, we lack the tools to actually understand those mechanisms. So, well, I want to understand how this works. For example, what is the role of spin coupling in this? What is the role of very much local and intrinsic chirality of one building block versus the global chirality of a morphologically twisted structure? I want to understand this, but we actually found there are not that good optical or any really tool to study this, especially transiently. And so we've been starting to develop such tools. Well, that's kind of where I'm coming from. And now I want to take a step back and kind of show you a little bit how we developed into this niche of trying to make new tools for the materials community. And it all started really with my initial research on these halide perovskite semiconductors. So who in the room has heard of halide perovskites before? Yeah, okay. Say a third or so. So very briefly, these are quite beautiful semiconductors. You know, we always imagine something like silicon or gallium arsenide when we talk about traditional semiconductors, and they are really hard to make well. Just to say, you have to work very clean and pure and make these very nice materials in a clean room. Use high temperatures, maybe 1,800 degrees, to make you a beautiful silicon wafer, pristine, and make it work well when you want to do things like solar cells or LEDs. And then such solution-processable materials come around, which are just you throwing together different precursor inks, these different ions in a little cocktail here. You have something like cesium, lead, bromide, or so. You know, you have a cubic crystal structure here. You have these corner sharing octahedra of these lead halide octahedra, and then they call it a cubic fashion around the central A side cation. That could be even something organic, something like methyl ammonium as a cation. You do it together, you spin coat or drop cast your little film, and you get a remarkably efficient, even flexible and ultra lightweight and thin solar panel or LED out of it. And that's really still magical to me how that can work so well. And yet, even after the last decade of research in this space, I would say we still don't fully understand why these materials can perform so well, despite them being so imperfect the way we make them. So this really started off a bit of the research, and this first of a few stories I brought with me today for you is that of the rather unexpected benefits from disorder. Disorder that we can well understand arises from the messy way we make these materials, but their consequences are really profound. So we now look at thin films of such semiconductors. We look at mixed halide, bromide, iodide, mixed ones, and we see that actually charge carriers, depicted here as electrons and holes, really are not seeing a perfectly flat energy landscape. They see a very heterogeneous hill and valley landscape. And that means some of them might get stuck and locally accumulate. So when I say it's very simple and easy to make these materials, I really mean very simple. You put a little droplet of your different ions on a spinning substrate. You heat the whole thing up to 100 degrees Celsius, something you could literally do in your kitchen, even though I advise against it because there's some toxic materials here. But you could. You shine with a UV torch on this, and you see you've already made something that is remarkably fluorescent, something that absorbs those UV photons from your torch and shines them right back at you, so you don't lose a lot of energy, it seems, to any heat or non-radiative losses. So this is really cool when we compare it to how we make a silicon wafer in the clean room. Still fascinating. Now, if we take a closer look at such a thin film after we've made it, and here I look at a methyl ammonium, formaldinium, bromide, iodide cocktail of ions, which works well. So mixed halide one. And when I say closer look, I mean we literally look at it with a microscope, a confocal luminescence microscope, then you might see something like this. You might see a very much not perfectly flat energy landscape. You see here the luminescence peak energy, so the color of the light that fluoresces at you, is actually varied by tens of milli-electron volts in domain sizes of a couple of microns or so. Again, very heterogeneous. If we then ask where does that come from, and we correlate this and overlay it with the chemical composition of the film, which we can do with a technique that's called electron probe microanalysis, basically a nice element-specific X-ray fluorescence, you will see that actually it's the local ratio of iodide to bromide building blocks in this iodide-bromide mixed film I mentioned that is varied, that is locally higher or lower. You have locally more iodide or bromide, and this actually modulates the band gap, the optical band gap that we saw in the map here. So this is where it comes from. Now, what does it do? I should say, people are welcome to interrupt me also during the talk and not just shoot at the end. So whenever you want.
So, if I may,
Ben, go for it. It starts.
ionic sparks have a somewhat lower bandgap and they accumulate more excitonic, and that's why you see high luminescence. Also, except for the spectral shift, you see high luminescence.
Yes, so the intensity would also be correlated with that, exactly. So I'm not showing here some nice drift diffusion recombination modeling that you can do to really quantitatively capture actually the intensity mapping, yes. But it would.
So yes, well, I mean, I can see on the right-hand picture that you definitely have a very heterogeneous composition of your material. However, if I look at the actual patterns that we get from the formal luminescence map from the electron probe, they don't really seem to match. Right? On the left-hand side, you see kind of stripy behavior, and the other one just says, yeah, it's not perfectly the same. So
I would say they match pretty well. So these are not the identical overlaid ones, so I should add that. So that would be, you know, you could do it if you wanted to really be good at it and use some gold markers, I guess, but we were too lazy for that.
That's
so, sorry, yeah. So these are not one-to-one the same identical film at the same position. It's just comparing features, but other people by now have done this direct correlation, so it's known business. So yeah, you can ask what does that do to your actual performance, because I opened up with saying we want to work on making solar cells and LEDs better. Well, a very good proxy of that to start with is something we call photoluminescence quantum efficiency or quantum yield, QI, which sounds fancy and just means the amount of light out divided by photons you excite the material with. Say 10 photons in, 8 photons come back out, 80% efficiency, fantastic. So we do this, but now we make it actually a measurement as a function of the excitation density, how hard we're exciting such a film. And we can see that for the prototype single halide, one building block only, methyl ammonium iodide, MAPI, in gray, eventually you see the luminescence efficiency drops quite steeply. That when you get below a certain excitation density, you might create those electrons and holes, those carriers you want to extract or have recombined in the luminescence experiment. But of course, this material has lots of defects as well, and so they eventually just get stuck and recombine non-relatively, and you lose your light output. That's bad news, of course, if you want to make use of this excited state that you've created. But interestingly, for all these mixed halide compositions, and I show here two in blue and orange, but really we looked through a whole zoo of different materials, all that have a mixed halide bromide iodide case with this heterogeneous energy landscape. They all level out actually at rather nicely high efficiencies, even for the very lowest of excitation densities. Now that's very useful, because if you think about it, you do not want your solar panel to only operate perfectly well under sunny conditions. It should do a good job under the conditions right now, cloudy, perhaps below one sun. This is kind of below here. Your LED display, you don't want that to run only well at very high charge current densities, because that would drain your battery life very quickly. It should do a decent management and efficiency even under low currents. So it seems this effect really is useful, especially for such real world below one sun conditions. And here I cut a long story short, we correlate all this with transistor measurements, with time resolved luminescence and transit absorption measurements, et cetera, to really show what's happening is a local charge accumulation effect, where even though globally your charge carrier density, isn't very high anymore if you excite with so little light, but locally these charge carriers can actually accumulate and therefore act as very efficient hotspots to be extracted from for a solar cell or to emit it from in an LED. So this charge carrier modulation effect actually enters certain regimes where it's actually okay to have disorder in a way, and it's not so bad. Yeah.
But these, let's say, local potentials, more charge carriers also affect Auger recombination. So they increase Auger recombination, which would lead to little bit more non-radiated.
That's also true, but then the Auger constants for these materials are such that we rarely enter. That would come into play at 10 to the 18 or so per cubic centimeter. Then yes, that would become problematic. But here we are so low, they don't really come into effect. And of course, yeah.
Great. If you have traps, isn't it a problem for PV performance?
Yeah.
So you want reduction as well as the capturing. So
you are fine if these are shallow enough traps that they don't completely kill your excited state over time. And of course, we extract here vertically, so the diffusion length is still okay even then. This effect for the solar panel, for example, only works. It's more subtle than this, of course. It only works when there's a difference between your trap density for electrons and holes. So basically what's for the expert kind of really going on is that we shuttle away the carriers from a higher density to a lower density of traps region. So, if I accumulate lots of holes here and there's actually a lower hole trap density, then it's a useful thing. If it wouldn't affect that, then it's just a redistribution. We wouldn't globally win anything. But that's fortunately the case for perovskites, so it does help you.
You showed us a landscape on micron scale. What happens more locally? If you have like SDM or something to tell you if this is locally homogeneous on nanometer scales, or if it keeps going,
it keeps going. So there's by now beautiful nano PEM electron measurements. There's nano XRD measurements. So you have heterogeneity on all length scales. You can zoom in to a nanometer grain, and even there you find kind of a surface that might be decorated with more iodide than the core of that grain, which might be richer in bromide and so on. So it's Sam Strengths did some beautiful work on that on these different length scales.
If you have from the modeling, can you tell which range of heterogeneity is actually useful? Because some of it might be detrimental, and you might want to make grains homogeneous with the microstructure.
Yeah. So this for now just relates to the bandgap modulation from the halide mixing, right? So this is kind of separate even from grains and from the microstructure or any other distortions and so on. So here I take the grains not into account, because they don't seem to matter so much. These bigger features on the micron scale from the halide demixing seem to matter much more. That's quite nice.
Maybe a related question. So since you have all these homogeneities, is it really fair to talk about the crystal, or should I really think about it as just small, very small crystals that happen together?
Yeah, so I would definitely, these are definitely polycrystalline materials. So they have their grain size for these might be 200 nanometers or so, little crystalline domains. And even then I wouldn't really call them single crystalline domains, because they're not. This is essentially polycrystalline. One can also do such measurements on mixed halide single crystals, but that's another story. So these are polycrystalline and partially locally demixed in the halide composition, and it modulates your charge carrier dynamics quite a bit, but not fully detrimentally, which was nice news, right? I'm not saying make your solar panel from silicon not well, please do, but if you can't, it's nice that sometimes you're lucky that charge carrier accumulation makes you not lose so much. So this was quite nice. It was, of course, a huge joint effort. I want to highlight Stuart, who's really driven that project, and all the people from Vanmaekelbergh and theory from David Beljon, TDDFT I didn't even show here. Henning Söringhaus did some beautiful transistor work for us, and so on and so forth. So big giant effort. Well, that's nice, and you could say, okay, well done. But then if we think about the solar panel again, I mentioned it's actually a vertical device stack. Often you have top and bottom electrodes where you want to collect your charges, your electrons and your holes. And now I'm just talking about some lateral mapping, which is all fun, but does that really mean a lot? So we then ask the question, can we also vertically kind of learn about how charge carriers are moving in these materials? And so we came up with a methodology that we hope is useful beyond just halide perovskites. We could do this with a silicon wafer if you want as well, on the vertical charge carrier tracking in semiconductors quite generally, using optical means. Now, how does that work, you might ask? Well, first, we need a thin film material, but there are quite a few. So we need to get some light still through and out. And this is really work led by Chang Soon, who's master here and is by now also an assistant professor in Korea. Fantastic guy. So we start again with our photoluminescence map. This time I plot here the PL intensity, not the energy. And we also, pixel for pixel, look now at the luminescence lifetime, which, just like the intensity, you can imagine from all this disorder and all these defects, is quite heterogeneous yet again. So the PL lifetime also is varied on this micron scale or so. What we now also didn't do before, is we don't just excite locally with our control PPI microscope and detect locally, but also away from the excitation center quite a bit. So now we can take into account, of course, phenomena like diffusion and recombination on the way before we enter that remote spot where we want to collect recombination hearing from. So from this, we can learn what happens across the excited state lifetime and over the distance. What we now also do is that we don't just scan away from excitation, but we also look at the luminescence from both sides of the film. So we don't just excite from this side and then collect from this side, but we can also excite from the top side, but collect luminescence from the bottom side. And again, this luminescence spectrum will be looking different. It will be probably redshifted because all this light must have now traveled through a lot of the bulk material. It might have been reabsorbed halfway through. It might have then re-emitted a photon again. It might have been trapped, might have, diffused further down. So from all these self-filtering and photon recycling phenomena that we can take into account using these different measurements, we can actually stitch together the full picture of how vertically the charge carriers must have moved through the system. So really, here you can now see a vertical carrier diffusivity map. And that's what is, again, heterogeneous. So more disorder. This time we look through the film, and you can probably rationalize this. I hope you see that a little bit here on this cross-sectional SEM image, scanning electron microscopy image. There are these buried grain boundaries even within the material, where you could totally imagine that the charge carrier has a harder time making its way straight through this if there's this grain boundary in the middle. So you can see the statistics here. It's really varied quite a bit, factor 50 or so, that you see higher or lower vertical diffusivity from pixel to pixel. So quite a heterogeneity here. Now you can ask, isn't that then very detrimental for our device performance? And the answer is, by modeling now all of this, so four-dimensionally in the X and the Y, and the Z, and time-dependent direction, we can say no. And we can say that also by looking at this. So you excite here locally at the top, of course, but then as 1, as 5, as 10, 100 nanosecond eventually pass by, you see that even though there are perhaps these hidden grains where you have a harder time to diffuse to the other end or make it to be extracted, there are then other much better suited grains that you might eventually move into through such a photon recycling event or simple drift and diffusion. And overall, across the excited state lifetime of the material and that we have at hand, and the trapped density it has on average, etc., we almost quantitatively collect all the charge carriers. So that's good news. This basically, again, rationalizes how we can get away with being so messy in the way we make the material. Yes, there are locally worse grains, but then there is also better ones. And overall, the performance is high enough that globally you extract the charge carrier typically within the lifetime of the excited state. So that was very reassuring news for people that want to make use of this solar cell stack. And that was kind of the second mapping story of the day. So Jack Soon was really leading this, but of course with lots of inputs also from Korean groups and Neil and Sam.
This fits with I think the fact that real photovoltaic cells, so efficiency is close to the Shockley Quasar limit. Because they are maybe a few percent low for the Shockley Quasar limit, which is kind of almost ideal.
Yeah, they are already quite good for perovskites. They are, and yes, and we could show that they really, and especially Changsun, that they really benefit already from a photon recycling effect quite heavily. So that from a certain PLQY onwards, they can show this quite well. So these materials are already also making good use of light management. Yeah.
Can you explain a bit more how you determine this vertical diffusion constant? There's a lot of modeling.
Yes, it's just a lot of modeling. So it's really just from all these individual measurements, from the distance-dependent measurement, we get more information about the diffusivity locally. From the just fluence-dependent time-resolved PL, we can get the trap density of the film. And then again, from the front and back side, we take into account photon recycling and self-filtering effects. So it's just one massive code in the end that Jackson developed that arrives at that, taking into account most of the effects that we can characterize.
So I saw on the previous slide that it seemed that the thickness of this film is a few hundred nanometers.
Yeah.
So to what extent can you still view photons that are emitted somewhere in a ray picture where they get reabsorbed later on?
Yeah, so that's why it cannot be too thick. So the moment it would be too thick, a material, we cannot learn anything from the backside measurement anymore, because then no light, when you excite from the top, comes.
But my question is, this is actually a thickness on the order of the wavelength. So can you view photons emitted from the top as like a ray that is emitted and it can be reabsorbed? It's not the wrong picture, it's not too thin for that.
Oh, no, actually, these are having such a high absorption coefficient that they all get very much quantitatively absorbed in the lifetime. So you definitely do absorb the majority of the excitation light. Yeah. So for these, yes, they are that good. A couple of nanometer is all you need to absorb all the light. No?
I can understand that if you come in with a plane wave, it's absorbed fully. But my question is, can you view emission? Like if two charge carriers recombine, do they don't have to create some kind of plane wave that travels through the? It's all sub-wavelength.
Yeah.
And you're talking as if there's plane wave traveling through material.
So there's a wave guiding effect to it. Yes, like that, absolutely. Like that. Yeah, but then eventually you can say also there will be a reabsorption event in the film, right? So that's reabsorption is happening in a big piece of semiconductor. So together you can work it out in the code. Details of the code, of course, I don't know by heart. But yeah, so the photonic effects are taken into account for the transfer matrix, and then recombination and re-emission events. Okay, so this was kind of the carrier dynamics or the background, because then it became interesting, and I wanted to ask the question: can we actually also map out spins in these materials? And that came from the promise that these are such heavy elements that they have strong orbit coupling, that you can get very nice selection rules in using polarized light to interact with spins in them. And so coming from this whole mapping idea, can we also follow those spins and map out spin dynamics in these materials? And could these materials be useful for spintronics, for example, using solution-processable materials? So the short answer is yes, you can. It was not super easy, but at the end it led to the observation of an ultra-fast spin domain formation in these materials as a consequence of local symmetry breaking. So you could say of yet another story of disorder and lack of perfection and crystallinity. So let's take a closer look and unpack that. We came from the initial idea of using a transit absorption measurement. So you have your pump pulse that excites your semiconductor, or maybe a molecule from a HOMO to a LUMO state, and then the time-delayed white light probe that is kind of a UV vis spectrum of your excited state, and you wait in time and therefore record a time-dependent excited state spectrum as well. Now, we can just chuck in polarization optics, and I just sketched that out here, even though in reality it's much, much harder to do that well, and instead go for circular polarized pump and probe pulses as well. Now, we changed our experiment slightly, but it has profound consequences, because in these halide perovskite semiconductors, it means now that the selection rules apply. It means, first of all, conservation of total angular momentum. So the Z projection of that is then the MJ state. And that means it has to change if I absorb the circular polarized photon of a given handedness. So it would add or reduce that total angular momentum count. And this is therefore leading to the valence and the conduction band really being split up into these subbands here. And to the fact that we can very specifically populate one of these substates. So actually it's a total angular momentum state, but I'll, for simplicity now, say they are spin states. How spin pure they are is still up to debate. It depends a bit on whether you look at electrons and holes. But we can, for example, use a left-handed, which I assign to sigma minus, and then right-handed to sigma plus. We can, for example, populate this one state here across. And we would have now created this substate. Okay, so this would add the +1. And then we could read out with the same helicity of probe this very same state. So a probe of the same handedness, again here sigma minus labeled, let's call it left at left or right at right, and that's co-polarized, would simply retrieve a normal transfer absorption measurement where you create an excited state, and then you can read out how long that's alive. So if you look at the ground state here that is bleached, and you will find that after some time it's less bleached. But what we can also, of course, do is we can excite this one state with a left-handed pulse, say, but then read out this other state with a right-handed circular polarized pulse. Now, we haven't populated that state to begin with, so at time 0, you also wouldn't expect to see anything there. And only if time passes by and there would be some sort of spin flip occurring, would you expect to eventually have populated that state and therefore see something there. And eventually, of course, spins would randomize and you would just throw out, and all of that would happen within your excited state lifetime. And this is not something we've invented. This has been shown by, Vali Badini, Matt Beard, some others, and is really leaning itself from the older spintronics folks. But it works very well for perovskites. And if you do that, you really see what I predicted would happen just now. That is to say, a co-polarized measurement here in blue would give you this prompt rise and then decays with the excited state. And the counter-polarized one really takes some time for a spin flip to occur to build up, and therefore has this delayed rise time here. And if you just subtracted co minus counter, you would be left with this sharp drop, which looks like mono exponential. And that would be really on the order of 2 or 3 picoseconds max for all of these materials. So this has been shown, and it is quite beautiful that you can just this simply optically read out a spin lifetime of, say, 3 picoseconds in this material. Okay, right. So now what I asked was actually, can we map this out? And that's where it gets slightly more complicated, because now we have to move to a pump probe microscope, the TA microscope, which leads me to introducing Arjun Ashoka, who's the real star behind this story, and who is just brilliant. And I'm very curious to see where he ends up in the end. Such a fantastic student. So Arjun's work. So we married now this polarization-resolved TA with a TA microscope, which we were lucky that there existed already one locally, so we could only walk in there and mess it up with polarization optics and have a hard time to recompress pulses and to not mess up polarization states. But in the end, we arrived at a circular polarized pump probe microscope, having diffraction-limited spatial resolution, actually a little bit better than that, and then importantly 15 femtosecond time resolution, and being again able to look at co and counterpolarized hand emissions. So what I plot now in the next step is the measurement, the mapping of such a pump probe experiment of a film of a halide perovskite. It's this one cesium MAFA iodide bromide. It's just a very well-known composition that works well and is rather stable. And I'll plot, for simplicity, just the green curve, so to say. So I'll plot already co minus counter of the TA perovskite bleach and divide it by the sum of the signals. So just net polarization response. Okay, so let's do that. And at time 0, the pump hits. And what we find is, rather unexpectedly, this strong formation of these different domains that are positive or even negative in polarization, and that outlast this measurement for quite a while. We are now talking 7, 8 picoseconds in. Remember, I spoke about 2 or 3 picoseconds max in the past for the bulk measurement. So this is very curious and unexpected. So let's try to understand how can this come about. So if you look at such maps now of these different polarization domains, positive and negative ones, you will find that the kinetics associated with every of these pixels is also vastly different. And you see that the positively polarized domains actually have prompt kinetics, and negatively polarized domains have delayed ones. Okay. Now, if you summarize over all of these pixels again together to retrieve the macroscopic response that has been previously shown by other people, we retrieve the green curve here, and that was very reassuring to see. It retrieves our macroscopic response. Within 2 or 3 picoseconds, the global response is really, we have decayed, it's over. But you see that locally, actually, we outlast for quite a while longer. And you would have missed it had you only averaged over the ensemble. So while this is still a bulk thin film, but it's a polycrystalline one, it reminds me a little bit about works by Freddie and so on, that the single feature microscopy revealed so much more. So this was reassuring and a light sanity check that we're not completely crazy here, and we kept on doing such sanity checks because we have to be very careful with polarization-resolved measurements. But okay, that's curious. So let's unpack that more. I can, of course, do this for every pixel so that you believe me. And I could ask you to correlate that in your heads, but I can also just do it for you, and you will see, okay, this is definitely correlated. So really positively polarized domains are those with very much prompter rise times than negatively polarized ones with very broad rise times. Okay, that is false. We can now also do another experiment where we locally initiate such a spin population and then look at globally how it moves in the film. And coming from a, say, PL microscopy background, you would probably expect a rather isotropic diffusion away from the center of excitation, perhaps, and this to broaden up. But if we do this, and I'll show you here the subtracted out response with some crosshair in the center, you actually see that we are moving to the top right corner of this plot. Can everyone see that here? So this is very much not just an isotropic expansion around the center. It's very much moving out. And that's very curious. So pardon the noise here, but it's very much robust if you do this 20 times over, that there's directional movement. And now this is getting very exciting. So why is there a directional movement of this spin polarized population? Okay, so there are two explanations that come to mind. The first one is to take into account everything I've told you about before in this talk, which is to say there's lots of energetic disorder that will drive all these charge carriers to just go downhill in energy. And, with diffusion, they will want to go downhill in energy. And yes, we have given them a certain spin at time zero of our circular polarized pump, but really they don't care about that. They just will want to flow anyways downhill in energy. This could totally be the case. Okay. But then there's a second idea, and that would be that because of all this disorder I spoke about, and because of all the symmetry breaking we expect locally, the moment you fully break inversion symmetry in the crystal structure and have these heavy elements and strong spool coupling, you could also invoke an idea of spin momentum blocking in such a rush-bar split system. Now that would mean that if I created a spin-up population, it would flow to this left side, for example, whereas the spin-down population would flow to the right. Then it's locked to momentum. Now, there's one easy way to check whether we are crazy or whether it's much more mundane than that. And that is to say, let's just switch the initial spin. So I just use my other handedness of circular polarized pump. So I don't initiate spin up, but spin down. And if it doesn't care about the spin, it will still flow just downhill in energy one way anyways. But if it does care, it now flows the other way. We didn't change anything else about the energy landscape. We just would change the spin. So interestingly, and I did really not expect that because I was so skeptical, it does point towards this picture more. So really, changing the helicity of the pump, the sign of all these polarization domains change. So whatever this little snake here in red becomes a blue snake, and so on and so forth. Again, you need the correlation to really make this a robust statement, but the correlation really holds that the domain polarization sign switches. What's even more in my face kind of supporting this, which is when I really started to believe it, is the kinetics. Now you can say, okay, you are still not good with your polarization optics, no matter how good you tried. This is just an intensity set. But all the kinetics that were previously associated, say, with the positive domain to be prompt are now negative domains, and they are also delayed. So this whole kinetic has also changed now. And that is not something you can explain by having been a little bit off with your polarization intensity. So the fact that all the kinetics changed as well really hinted at this being very much not an artifact. Now, how can we piece this together and explain it? But domains and spatial motion and kinetics switch. How can we explain this? It's actually a rather simple model, but it should be enough to explain this. So I want, first of all, for my recipe, spin momentum blocking as the rule of the game. Spin up goes this way, spin down this way. Okay. And it has to come from somewhere. Let's for now be agnostic about the origin of this inversion symmetry breaking, but let's say it's there. And what I then say is we just define two neighboring grains here with locally different direction in which the inversion symmetry of the crystal structure is broken. So let's say the one grain is strained in this way, this octahedral tilt here, or this little deformation, and in the other neighboring grain, it's in that way, and they have therefore different spin textures also locally. Sketch kind of here. Now, what will happen if I just flood the whole system with a circuit polarized, say, right-handed spin-up population at time 0 is, of course, you will also get this polarization response. So initially all blue shown here in this positive polarization. But what that now means is, of course, that in the left grain, where I have a certain spin texture, this might mean the spin moves to the right, whereas in the right grain, where I have another spin texture, it might move now to the left, as the local rule of the game dictates by spin momentum locking. Okay, so what now happens if I wait a little time is a spin scattering event will occur. And what happens then? Once I wait, say 250 seconds, I spin flip into the other subband. And what that now means, of course, that also, again, my rule of the game has changed. So I will now, if I was spin up and then now spin down, I will also now want to flow into the other direction. So you therefore start to segregate out here and change directionality. And this is exactly what we see. So after some time delay, after the spin scattering has occurred, we therefore get this polarization pattern to develop. And of course, if you then switch just the initiation, so you just go to the other handedness of pump, so say from right to left-handed, then everything changes. So your initial rule of the game is maybe to go this way, but then after a spin flip, you will go to the other direction, etc. And the global pattern subsequently changes, flips. This is all it takes, really. So spin scattering after some time, and this inversion symmetry breaking that I've kind of just a priori now predicted to be there, apparently. So the last thing is, can we find measurable signatures of such local inversion symmetry breaking to give rise to this spin momentum blocking? And we think we have identified a few cues for this at least. So here you can see, for example, the piezo force microscopy vertical phase, which is varied quite a bit and actually shows some hysteresis. Not an expert in this. This was done by collaborators, therefore with a pinch of salt. But what I find a very direct and robust mapping technique actually is just cyclic harmonic generation, because we probably, most of us have learned at some point that SHG really needs to have a non-zero second order susceptibility to show up. In other words, inversion symmetry breaking, be that at an interface or be that in a really inversion symmetry broken material. And again, we see a nice and strong modulation of this SHG across the film, which totally says there is differently inversion symmetry broken local domains. So you can rationalize this with many different literature reports. This was very nice by Sam Strength, for example, where they really look at such very small nano XRD kind of domains that they map out and where they show different octahedral tilts and directions where it's not a perfect inversion symmetric crystal structure that I showed you in that first sketch. We can then model this a little bit. Here we set up this polycrystalline structure now with different domains using Voronoi tessellation. Is a little bit overkill. And we can just say I give this one grain one spin texture and the next grain the other spin texture. And then I just flush the whole system with say spin up population at time 0, and I'll just see what happens. And again, you will see in this little Monte Carlo toy model that as time passes by and the scattering events occur, as we approach this, we actually segregate out and really form these domains quite neatly. Of course, with that, we can very robustly and very easily model all these maps in all the different handednesses and so on. So that's kind of all it takes for this. So to summarize this last big chunk before I do some more outlooky work, we see actually formation of these spin domains and also signatures of local inversion symmetry breaking, which, to be honest, are not very surprising. Had you asked me after the first 2 parts of the talk, is this going to be a perfectly crystalline material or an inversion symmetric one, or likely not, I probably would have also hinted at it's probably messy and not very symmetric. But that's quite cool. So, okay, and it's again big collaborative effort with all the groups involved, and Arjun really spearheading this. So this was now, if you will, a transient circular dichroism mapping of some sort. Actually, it was still an achiral material where we just initiated the spin population using a circular polarized pump and then read it out. But it begged the question, can we also look at luminescence behavior? And this is where I then kind of found it gets even harder to do this right. And the last couple of years with my group at Harvard, we've really started to develop mostly techniques so far, because again, there isn't good techniques to do this well. So we started with static circular polarized luminescence, CPL. And I want to briefly just showcase that Vinald did a fantastic job in putting this piece together, which was meant to just serve as a little review for us and everyone else on what's going on, but really turned out to be a much bigger project. So in this one, you will find a lot of artifacts that you should watch out for if you want to characterize your material with respect to its CPL. Again, you have to think about things like self-absorption phenomena. Something might look like it had CPL, so dissymmetric left versus right-handed emission, but really it might just have circular dichroism in the absorption. And your emission coming from further inside the material means you experience the dissymmetric absorption of the material itself before you get out, and then are detected as apparent CPL. There's other things like the combination of linear dichroism and linear birefringence that gives you apparent CD and CPL phenomena as well. And then it gets a bit nerdier if you're really interested in things like how the photoelastic modulator modulates a response in a typical lock-in based technique. You have to be wary about the non-sinusoidal response of this PEM modulation. So you have to think about actually correcting for it, which you would need an n-order Bessel function of the first kind for. But if you do not, you actually miss out on the 10% or so. It's really not that trivial to do right. Phase offset calibration is probably something most people will never have even looked into. And so what we actually ended up doing is not just talking about how to measure right and how to avoid artifacts, but also wanted to give the community something, because for everyone who's at least the PI and looked into price tags of CPL spectrographs, we are talking about the bigger six-figure number. And so here we've now built a tutorial with this open access paper that allows you to build your own for a small fraction of the price, a factor of 10 down. And importantly, we also have on our GitHub the whole code to really interface all the different components. We list exactly what components you need to buy for cheap and how to interface them, and then run the code to really also run your measurement. And what it also has, which existing commercial CPL spectrographs did not have, is a built-in linear artifact flag. So that's one of the predominant artifacts, is linear polarization that looks like circular polarization, because it will still get detected. So we have built a little linear polarization red flag that will show up if your perovskite thin film is actually just a bit strained, and therefore gives you a little bit of linear polarization and you thought it was CPL. And this has now been also implemented by one of the bigger CPL companies. And so they use that as well now as a code. Fortunately, we did not patent this, or we want to be nice, so let's put it this way, so it's for free. The companies now use it, which is a good thing. So since then, and this is the very newest and last little outlook before I'm done, we have ventured on to really do transient CPL, which there isn't any good one, and we've really looked into the literature. You can easily just chuck in a quarter wave plate or so and hope for the best, which is all fine if we don't want to add the word sensitive. And also fine if we don't want to add the word broadband. We now talk about the full broadband visible spectrum, sensitive CPL spectroscopy. And sensitive means 10 to the -4 dissimilarity factor, which is what a traditional, say, halicine chiral organic molecule would show you. And 10 to -4 is not something you can measure with just rotating quarter wave plate. And that's why usually you use a PEM with lock-in techniques, which you can't do if you want to be A, broadband in the measurement, and B, time resolved. because that's not feasible. So, and just to make it even a bit harder for this fantastic postdoc that is Antti and built this for the last 2 years, we wanted to also get the full Stokes vector recorded. So the complete polarization state characterizing the photon, not just whether it's CPL or not, but really, the way you can plot an electron spin on a Bloch sphere, you can plot the Stokes vector of light polarization on a Poincaré sphere here. And we now read out the complete polarization state with the sensitivity and broadband and nanosecond resolution. So with that, you can, for example, I'll spare you the details. It's been very hard, very challenging. You need to do full millimetrics formalism for it and account for very many artifacts that are not trivial to account for if we want to talk about 10⁻⁴ sensitivity. Really, the sensitivity difference between 2 pixels on your detector matters a lot. It's a nightmare, but now it's working. So the patent is still reading. We cannot publish it yet, but once the patent is done, don't move patents between continents and between universities. I do not advise you to do that, but once done, we can finally put this thing on archive. And so really, you can now look at the excited states, the symmetry or chirality, and look at the Stokes vector for these 2 different species, for example, decaying encoded in time, in nanosecond time steps here, and following different trajectories on their Poincaré sphere. So you could really distinguish how they develop, how they become less CPL active, maybe more linear or elliptical, and that's quite powerful. I'll spare us details, but even something that's the most studied CPL emitter, I think, which is the UFACAM, the European complex, even in that one, we actually saw new features that in the 50 years of publishing on this Drosophila of CPL people hasn't been picked up, which is quite fun. So you see these hidden European higher energy lines. We can nicely distinguish between the linear components from the photoselection in the ligands and the circular components, which are in the European emission lines, and really be clean in the way we characterize CPL. So I think that will be very useful again for the community in whatever they want to research. So with that, I want to wrap up. I want to say a big thanks again for the teams involved in the transient CD mapping in the end, and the transient and static CPL teams, and the whole team involved in the project. And of course, you very much for your attention. Thank you.
Thank you very much, Sascha, for this advanced experimental research where you go further and further.
We try.
So this looks impressive. We had already a number of questions. Probably other questions from people.
No, it's fine, because it's Friday afternoon. You asked already.
Yeah, so you mentioned you were initially skeptical about the cluster splitting, and I know you've been skeptical about that mainly because of the high recombination in the perovskites.
Yeah.
Can you comment on that?
Yeah, so I'm still skeptical, especially about big claims on say, large Rorschach splittings, and I think most have been debunked. There was some nice-looking ARPAS works that have been shown to be not real. So I think it's not a big number, and funny enough, from the speed of motion of our spin packets, we can actually do a back-of-the-envelope calculation on the suggested Rorschach splitting that would dictate such a movement. And actually, that is in line with, rather pessimistic small Rorschach splitting values. But it's also nice to know that it's in line with that and not with big claims. So if it's there, it's small. But there is hope, because this was a material that wasn't chiral by design, right? This was just a locally perhaps strained and disordered material, polycrystalline, where again we are agnostic to the origin of it. But I have therefore hope that with a by design made much more distorted crystal structure, we can also really leverage this effect to be much stronger. So skeptical for big Rorschach splittings in normal 3D perovskites, except for smaller modulations we picked up here, but hopeful for 2D strongly twisted materials.
Maybe first material and then material.
There are a number of different versions of why the perovskites are so resistant to solder or so beneficial for them. You have your own take on this and why it's, I mean, all materials can be made properly sorted, so how come in this case it works? Is it really unique or is it like a recipe for anything else?
I think, so it can be understood, I think, very well by now from the basic point of view of the band structure. So this material has a very nice band structure where the typical culprits of defect states are actually hidden in the bands that are occupied. So therefore, the usual killer traps in silicon or gallium arsenide are not going to kill us here, simply because they end up being in the bands and therefore saturated. So only some shallow traps that are.
But there's also some things about like mechanical elastic properties.
Yes.
Drawing atomicity, they kind of favors other types of transport and lower information.
And that's exactly the other one. I'm not deep enough in that. I love reading about the works from people like Vanmaekelbergh, for example, doing beautiful works here. And I think there is definitely something to the softness of this material, yes. But even just from a, again, defect point of view, it makes sense, I guess, because if I break a very much covalent semiconductor like gallium arsenide or silicon's highly covalent, then I'm left with these horrible dangling bonds that are killing things off. Whereas here, I'm ionic and soft, and ions move. And yes, that's bad for hysteresis, but maybe it also helps in not having so many of these deep trap states again, which would come from dangling bonds. So I probably could again relate a bit to electronic phenomena. And yeah, we did some work on photon information as well. That could also help protect your excited state even more. But that's yet another talk. And yeah, I think we haven't fully understood yet the material, but the combination of things makes it unique. Maybe not one thing, but I guess the combination makes it unique. Then, Alphonse?
Yeah, you almost partially already answered, but I wanted to ask the reverse question.
Yeah.
You beautifully shown why all these defects hardly matter. Is there still anything to be gained if you would do perfectly stoichiometric, perfect single crystal, defect-free material, perovskite material?
Yeah, so, and people still want to become better. People still keep on passivating the material to reduce the remaining trap density to nil. And you still will get a Nature or Science paper if you break the record by reducing it even more. And the records keep on coming in every now and then, but we talk about, a 0.1% performance gain. Does that matter? I think not at all. We have now reached a very good level of performance that is completely sufficient for having it on your rooftop. Now we need to work on stability. So the whole thing should last for 30 years on your rooftop. Toxicity, you don't want it to break up and leak lead into your water flow. But if you ask me personally, I think the days of having to tackle the defect density are almost over. Now it's stability work and engineering.
Even in silicon, it's always have been a sport to increase efficiency with 0.1% and having a new nature paper again.
Yeah.
Even if it is as old as.
It will keep on coming. Yeah, it's fine. And again, you win, of course, because efficiency is the one number you always want to get higher, right?
I agree that stability is here a much more concerning problem for all.
If it goes to a much higher cost of producing, of course, then
it's not worth it. Yeah. Even now already, which is a bit sad, right now already the bottleneck is not manufacturing, but installation and then assembly of the panel. So even now already the material doesn't matter. So basically we are really limited, if now speak about that sort of stuff. We are limited by politics, by how silicon is subsidized right now, and by cost of installation and manufacturing, but not of the actual material filmmaking.
Yeah, really.
So in these experiments where you created these spin polarized domains, do you need to do spin polarized excitation, or can you use linear polarized excitation?
No, if you do linear, then you would again just populate the left and right branch at the same amount at time zero, right?
So what? That doesn't matter, right? Because you are creating them on the 3 vectors picosecond timescale anyway. and they separate.
Yeah. Or well, that you create them, yes. Yeah. But I mean, that's what I just want to say is that's the way we see that. Therefore, it takes time for these to form.
Yeah.
Yes. No, you're right. You can also instantly flush both states at time zero. Yeah. That would happen with linear progress.
But you didn't actually do.
We also had a control experiment, I think. Yeah. And that, but then, yeah, it's not unexpected, right? You just populate then both states. And then, yeah, you look at any of the two bleached ones that you want to look at. Yeah. So that you could do. But it's more fun to, say I want to populate almost to 100% one at time zero. That's kind of the more precise you can create one spin population at time zero. I think the nicer it is.
I had a small question myself. You spoke about the first part of your lecture about how to measure the spin lifetime, the spin flip, and this was quite relatively fast. I forgot the precise number.
3 picoseconds, let's
3
say.
picoseconds, and then you showed this later on, probably more or less in the same material, this diffusive segregation of spins. There's not a competition because if you have fast spin flips, how can you then segregate? Well, you can clearly, but
it's funny, right?
For me, is the explanation of that.
So yeah, so the from what that points towards, the spin scattering event is actually needed to form the domain to begin with, right? Because if I go back to my sketch without them, you wouldn't have even had the chance to form. You wouldn't have had the chance to form positive, negative domains. So without the spin flip here, you would be left with just positive signal everywhere. So we are resilient and in need of the spin flip due to this order to even occur. But yeah.
But if you have a segregation and you have a population of several spins and they start to show spin flip, you lose them. So how can you maintain this for a while?
Well, you don't. If they flip into the other state and they're still precisely in that state, then you haven't fully lost information yet. That's kind of the difference, right? So it's then just moved into the other subband. So therefore, it's still very much there. And if you average over all of them, the net response will be 0. That's what we saw globally. So globally, it is 3 picoseconds, but the intrinsic response seems to be longer than that. That's how I would read the data from. But I should add, we are very far from understanding the spin physics of these materials, right? These are some first experiments, and we don't understand even from theory yet completely. For example, what is the way we can spin flip, and how does spin depolarize? What's the component of dephasing, and so on. So this is all still in the making, and some people, including us now, want to apply magnetic fields to learn a bit more about that.
Yeah. Okay. If there are no further questions anymore, I would thank again Sascha for this fantastic